I'll give you guys your test back at the end of the class. Let's talk about some things we spoke about last time, just to kind of segue into what we're going to be doing. We're going to learn to compute all sorts of integrals today. That's what we're doing in this class, so let's just review what we've been doing so far. Last time we looked at the area under f of x on the integral AB. And we had a notation for that. That was this thing, called the integral from a to b of f of x dx. So that's one thing that we found out about last time. We also found out about an algebraic way to compute this. We also mentioned there's something called the fundamental theorem of calculus, which says we can actually compute this area using the antiderivative of a function, where f is continuous and big F of x is an antiderivative. So the area under the curve, and remember how we did this, we erected a bunch of rectangles and we counted up the area under all these rectangles, we added them all up and we got an approximation for this. And if we take an infinite number of rectangles, we get the exact area, and this was the expression used to describe that fancy S for sum from A to B of all these f of x and change in x's. And that was the area under the curve. Fundamental theorem of calculus says we can actually compute that using the antiderivative. And we also spoke about the indefinite integral, so that's the next thing we spoke about. That was the guy, this integral of f of x dx, where the limits were not specified, but we also kind of realized that we could take this to be, in light of the fundamental theorem of calculus, we could take that to be the antiderivative of the function plus a constant that might have died when we differentiate. So now we're really going to be focusing on kind of like this guy, and then we'll compute some of these guys. So the idea here, we can compute integrals by reversing a sort of derivatives. So every time I gave you a derivative rule, I was in fact also giving you an integration rule, because they kind of went backwards. It's sort of, because it's not, you won't get exactly the same answer. There'll be some information that's lost when you differentiate that you may not recover when you integrate. But essentially, the idea is to compute this, we can find this, where this is just some antiderivative of that. So whatever rule I use to differentiate this to get that, what I want to do is reverse that rule to get back to the original. That's sort of the idea. And that's actually what this fundamental theorem of calculus comes in two parts. This is one of the parts, and the other part tells us exactly that we can actually reverse these two guys. The other part says that the derivative of an integral is just the original function, and so the reverse works exactly the other order. But that's kind of where we were yesterday. We talk about a lot of areas. We introduced this new notation. So basically now this leads to some basic rules. Basic in the sense that these would be the easy ones, the low-hanging fruit that we can get pretty much easily for free. So one was the idea of the power rule, and this is one that we did introduce last time. We're going to do some more, where I wanted to find the integral of x to the n, where n is a constant, x is a variable. And we realized that, hey, we could do this by reversing the power rule. Add 1 to the power, divide by the new power. Because what we did when we took derivatives was we multiplied by the old power and then subtracted 1. So now we add 1 to get back the old power and divide by the guy we multiplied by. And that leads us to this. It's called the power rule for integrals. It works if your n is not equal to -1 because otherwise you divide by 0. And this is referred to the power rule for integrals. There are other rules. So for example, if your n equals -1, we'll have to deal with that separately. So notice that if I'm considering x to the -1, that's just the same as 1 over x. And so the rule, this rule takes this form. Integral of 1 over x dx. What do you think that is? Right. Right? We know that if we differentiate ln of x, we get 1 over x. There's one caveat here. This rule is a little bit special because yes plus c, but there's something else entirely. There's an absolute value in this case. When you're reversing it, you get an absolute value. Why? Because if I just look at 1 over x, the x can be positive or negative. There's nothing restricting it there, as in the ln. But the ln can't handle negative numbers, right? So we have to worry about whether our x is negative. And it turns out that absolute value of x actually fixes that problem. Why? I mean, to realize why this is true, you just have to remember what absolute value x means. This means it does nothing if your x is already positive, so that's ln x. But the x is changed to negative if your x is negative. Obviously it's not defined at 0. The original is not defined at 0 either. But you'll notice that if you took the derivative of this, in the top, it's just 1 over x, as one would expect if your x is greater than 0. In the bottom, using u prime over u, you get -1 over minus x. So it gives you 1 over x again, if your x is negative. So whether in the positive or negative case, differentiating this guy gives you 1 over x. And so we need the absolute value to deal with the case when x is negative, and it works out fine. And so that's why I said sort of. There are some nuances in some places. That's one of them. We can also reverse something like, what's the integral of e to the x?
E to the x?
E to the x, right? Derivative of e to the x was e to the x, so as you would expect, the integral of that is e to the x plus a constant. There's a meme that goes something like, no matter how hard e to the x tried to integrate with the other functions, it made no difference. Never mind. Never mind. We're moving on. Grown. Okay. We can actually also integrate a to the x, so something like 2 to the x or 3 to the x or some constant to the x. This is a to the x divided by ln a, because you may remember to differentiate a to the x, it's a to the x times ln a. This one we can sort of justify with substitution, but I'll mention it anyway. If I have e to a constant times x, this is the same as 1 over the constant times e to the constant times x plus c. Of course, they're constant not equal to 0. So for example, I mean, I'll give you examples for a lot of these, but for example, if I have the integral of e to the 2x, that's just going to be 1/2 e to the 2x plus. And you'll notice that if you differentiate this, you get that. So these guys, I call these our basic rules. 3, 4, 5. These are the rules that we know now, by the way. We have this memorized, it is internalized, and we know these now. So we know these rules very well. We've been using them pretty much backwards for the entire semester, but now we want to go the other way. So we're going from derivatives to integrals, and we kind of want to think of them backwards. And you can think of every derivative rules that we did, the reverse of that rule is an integration rule. And so all of these kind of just fall into our laps right away. So basically if I want to find the integral of some random function, the idea is, and again, we use these rules like any other rules, they are templates. We need to make sure our rule fits on top of one of these templates in order to compute it using the right side. So let's just do some examples. Where do I want to list this? We're going to do a bunch to get a lot of practice in. Those guys. Start with A. Okay, what rule can we use here? Power rule for integrals looks like x to the n. So what I'm going to do is that's just, I'm going to add 1 to the power, divide by the new power, c. And so that's x cubed over 3 plus c. That's the answer. And that's it. B. It's cubed dx. Same thing, you apply the power rule. Not so bad. No, I don't trust you, Javon. You got something up your sleeve. It's not this easy. I know you're going to come with something. No, studies. Okay. C. Okay, now this one looks sort of complicated.
Yes. Is it x to 3 over 2 over 3 over 3?
Yeah, so the idea is, again, we don't have a rule with our radicals. The rules are our template, so we want to rewrite this to look like one of the rules. So I would rewrite the radical x as x to the 1/2. Now it looks like a rule, x to the n. And so what I do is I add 1 to the power, so that gives me 3 over 2, divided by the new power, that's 3 over 2. Dividing by a fraction is the same as multiplying by its reciprocal. So this would be 2/3 x to the 3 over 2 plus c. So of course the idea is something doesn't look directly like a basic rule, you want to use your algebra. You're going to have to remember all your algebra rules and all that stuff to simplify. You can simplify things to look like one of the basic rules you know. So if you see a radical or some sort of other symbol, you can use algebra to try to rewrite it into a familiar symbol that fits in with one of the rules, one of the templates. What about D? Yeah?
Can you rewrite it as like 1 plus x to the negative 1?
Sure. So that's a fraction. So we can split it across the numerator. That's just 1 plus 1 over x dx. And again, we're sort of reversing derivatives, so your intuition would be correct here. It's actually a property we could write down. That to find the integral of a sum, you just find the sum of the integrals, right? Same way you find the integral of the derivative of a sum, it's the sum of derivatives. It actually expands. You can just read it. So what you want to do when you see something like that, you do them one at a time. What is the integral of 1, and what is the integral of 1 over x? And then you add them together. So what is the integral of 1?
Just x.
X, right? A couple ways you could see that. You could just remember, oh, every time I differentiated x, the answer was 1. So the antiderivative of 1 should be x. You could also sort of think of the 1 as x to the 0 and apply the power rule. It is actually a basic rule that applies here. The integral of a constant is just going to be the constant times x because of the power rule. So the antiderivative of 1 is x. What about this guy?
Lx.
ln of absolute value of x. Right? The absolute values are important in this case because the sign of the x could change. So again, have something here. Looks kind of complicated. Simplify it first. It's actually, you can apply the basic rule to all the cases. You always try to simplify first. It's make your life a lot easier. Let's do E. We're looking at a sum of things now. Okay. I can rewrite it because there is no rule that looks like that. What about this?
2x minus 2.
Now it kind of looks like, this looks like the power rule, this is like the power rule. We know that the derivative of a constant times a function is just a constant derivative of a function, so the integral is going to behave the same way. So I can just leave the constant alone and integrate the function and it will work out. So we do these again one at a time. So this is going to be add 1 to the power, divide by the new power, which means you flip the fraction and multiply, plus 3 times add 1 to the power, you get? No, be careful.
No, negative
So
1.
I was going to mention that. That's actually a pretty common mistake. People just get into this idea of adding 1 and they just up the number. Be careful when the number is a negative. You should be subtracting. So it's a minus 2 plus 1, it's a minus 1. Be careful about that. And that's plus c. So I could actually, that's 2/3 x to the 3 halves minus 3 minus 1 plus c. So be careful with that little hiccup. That's more common than you realize. Okay. F. Let's talk about F. What are we doing?
Can we just like rewrite everything?
Rewrite it. And antiderivative this?
3 to 3.
It's just the same, right? Because the derivative would make a difference, so that's not going to make a difference. This one, you add 1 to the power, so you get
Minus 2.
minus 2 divided by the new power, minus 2. And so that just becomes 3 e to the x plus 7 over 2. Let's look at G. Now the function itself doesn't look that complicated. In fact, we actually dealt with it before. But there's a difference with this one. It has numbers on the integral. See, you remember what we call integrals like this? What are they called? They're called definite. So here we realize that this is a definite integral. But never fear, the fundamental theorem of calculus tells us how to deal with those guys. So the fundamental theorem of calculus says you can compute a definite integral from a to b by again just finding the antiderivative and then plugging in. Ultimately, it becomes this f of b minus f of a. So you take the antiderivative, you plug in the top number, minus the antiderivative, you plug in the bottom number. Notation-wise, there's an intermediate step that we customarily take here. We just, again, find the antiderivative in the same way that we've been doing this whole time. So this would be your big f of x. And we do this notation, we draw a long straight bar on the right side, put an a down here and a b here. And so that kind of signals to you that you take the top number, plug this in, then you take the bottom number, plug that in, it becomes this. So this here is just, it's basically notation to do that. So you don't put a plus c, you put a bar and you put the numbers on the bar. And that signals to you, I'm not finding an indefinite integral, I'm finding a definite integral evaluated at these endpoints. So let's do that here. So we have the integral from 0 to 1 of x squared dx. That is going to be equal to. And at first you ignore these numbers and you just find the antiderivative as you normally would. It's a power rule that applies to this guy. Add 1 to the power, divide by the new power. But then what you do, since there are numbers here, you write a bar, 0 to 1. Right? So you don't write a plus c. The plus c actually doesn't matter, because when you start subtracting these, you're going to have the plus c minus the c. It's not going to even matter. So it doesn't even matter for you to write it. And so now what we do, take the top number, plug in for the x, minus parentheses, just to be safe. Always causes a lot of trouble. Bottom number, plug in for the x. That gives you 1/3. Quick question before we move on. Or direction. Interpret that 1/3. What does that mean, the 1/3? I computed the integral from 0 to 1 of x squared. The answer was 1/3. What does that mean? What does it mean to say that the integral from 0 to 1 of x squared is 1/3? What am I saying? Yeah.
Is it the area under x between 0 and 1?
Right, the area under the curve. That's what this meant, right? Last class we introduced this as being symbolically what this is saying. This is the area under f of x between a and b. So this basically means that the area under y equals x squared on 0, 1 is 1/3 in whatever units you're using. So if you look at this function, y equals x squared, looks like that. But you don't care about the area from 0 to 1. That's your area. It turns out that a equals 1/3 would be the answer. So that's how you'd interpret that number, right? It's just the area. And one thing you should know about the area, I probably won't give you a problem where you have to worry about this, but earlier when I mentioned the area under curve, I actually put the area, the under in quotations. I don't know if you noticed, but that's important. When we say that this guy here equals the area under f of x on AB. Specifically, it's the net area is how you want to think about it. Meaning if your function is positive, then yes, it's the area under the curve and above the x-axis. But if you remember how we were setting up this integral thing, right? So let's say here's A and here's B. What we did was we put rectangles here to approximate the area. Right? But the height of our rectangles was determined by the function itself. So it turns out if the function ever goes negative, when you find f of x for that x value, it gives you a negative answer. Right? So it turns out if your function is under the x-axis, it gives you a negative area. Right? So it really gives you the net area with the x-axis. So if you're above, it'll give you positive answers. If you're below, it will give you negative answers. And what it does, if you have an interval where a part of your is above and a part is below, it'll actually subtract them. Right? So if this here is like the first area and the second area, then it turns out that if you compute this guy, it will actually give you area 1 minus area 2 would be the result. So that's just something you have to worry about. And if you care about the area that's bounded between a function and the x-axis, all you have to do is just to realize that you just split the integral up, compute the area from here to here, compute the area from here to here, and just know that on this side you will just take the negative of the answer. But that's a technicality. You won't have to worry about that, but it's just something you should know. So whenever there are numbers on our integrals, we can interpret it as the area under the curve, the net area, in fact. So we're A, B, C, D, E. So we're up to H. So this is another definite integral, which means it can be interpreted as the area under a curve between 1 and 3. That function is more complicated than I'm willing to draw, so. But we don't even care what it looks like. We can use this computation to figure out the area under that curve. Again, you see something over 2. It's the same as multiplying by a half, so that's how I would think about it. And so it's just a constant that you can just leave alone. And so integral of e to the x,
E to the
e to the x, integral of x squared,
x is over
x cubed over 3, and you put that bar to say we're going from 1 to 3. So what that means is we plug in 3 for x minus parentheses, plug in 1 for x. So this becomes a half e cubed plus 9 minus a half e minus a third. It's just like a half e cubed minus e plus 26. That would be the area under that curve between 1 and 3. Let's jump into the next one. And what do I do there? It's absolute value. You remember? So you brought it up because you're thinking of using the power rule. The thing is, it's in a form 1 over x. If you bring up and use the power rule doesn't apply for the power negative 1. So I actually wouldn't rewrite that. It's usually if you have something over x to some other power, you would rewrite it. But this you kind of think of it as 3 times 1 over x. Because we have a rule for that. That's just 3 ln x. Between 1 and 4. So I can plug in 4 minus 3 ln 1. Absolute value of 4 is just 4, and absolute value of 1 is just 1, but just be safe. What's log of 1? Ln of 1?
0.
0. Log of 1 is always 0 for any base. And so now we just have 3 ln 4. So that's the area under that curve between 1 and 4. Are we okay with this? Of course, it's not always going to be that easy. Like, I knew it. I knew Joanne was going to come. No, but seriously, it's not always going to be this easy. Not everything you'll be able to simplify nicely and apply a basic rule. It's not always this easy. Look at something like this, for example. Now it turns out that that guy, hopefully you don't have the urge of thinking that you can take the radical of this and radical of that and just expand, because that's blasphemy. That can't work. You can't distribute a radical across a sum. So right here we're kind of stuck. There's nothing really we can do with algebra to kind of simplify this to look like a basic rule. Like, this is under a radical, there's no way I can break that out into a bunch of fractions and distribute things. So doesn't look like a basic rule. And worse, can't simplify to look like a basic rule. And this brings us to 5.4. We skipped 5.3. We're going to go to 5.4, substitution. So we had basic rules for like the power rule and integrating 1 over x and integrating e to the x, and those are just rules that dealt with individual functions. And you might start asking the question, is there a reverse for the product rule? Is there a reverse for the chain rule? Is there a reverse for the quotient rule? And the answer is kind of yes. The answer is yes to all those things. Substitution is really the reverse of the chain rule. As for the reverse of the other more beefier rules like the product rule and all that, that's stuff you do in Calc 2. It's not stuff that's typically done in Calc 1 class. That would be called integration by parts. I was going to cover it if we had time, but it's not typical to cover it, and we won't cover it. So this is the reverse of the chain rule, basically. So it deals with when you have like a function plugged inside of something, as we have here. This function 1 plus x squared is inside of a radical. So substitution is how we deal with that. So theoretically it's the reverse of the chain rule, and I can tell you all about that, but we'll use it as an integration technique. And aside from applying a basic rule, this is the only integration technique you'll need to know in Calc 1. So you don't have to worry. There are many more, but this is the first one, and it's the easiest one to apply. So they usually throw it in Calc 1. So here's the process. Given f of x dx difficult to compute for us means it doesn't fit a basic group. I can't just apply one of these formulas that I have a template for. So here's how you can do it, the method of substitution. So you always try to simplify first with algebra, but sometimes that doesn't work, as it doesn't work here. And so if that doesn't work, here's going to be the method. I'm going to describe it in words, which might be confusing at first, but when I actually do the example, it should make it a little bit clearer. But even then, it might be a little bit muddy. Like substitution takes some people a while to catch on to. Took me a while when I learned it the first time. I'm not sure why. But after a while, it was like, oh my god, this is the easiest one. Like out of all the integration techniques, this is going to be the easiest one if you ever have to move on forward. But the first step is the following. You substitute an expression for a single variable. Customarily, we use u. Right, so we usually use u to represent this expression we're substituting. We call it u. A lot of times, for that reason, people call it u substitution, but technically you could use any variable. U is just a customary thing. But you do it with accomplishing two things, two goals that you want to apply here by doing the substitution. One, it should make the integral simpler. Simpler for us means looks like a basic rule. The goal is so you want to transform it to look like a basic rule, but algebra won't get you there. But you essentially want to make it simpler so that you could use algebra to simplify. Two, in order for this to work, this has to be true. The derivative of the expression must be a factor elsewhere in the function. So we're going to substitute an expression that's hopefully going to simplify things for us, but at the same time we need to make sure the derivative of whatever we substitute, I can find it somewhere else hanging out in the function. If it's off by a constant factor, we don't care. It's basically just the variable part of the derivative. Off by a constant factor is okay. Why? Because with derivatives we can always factor out constants. So a constant factor being off doesn't matter to us. We can just always factor it out. So that would be the first step. You have a complicated integral, doesn't fit a basic rule. First thing, you try to force it into that way by substituting an expression that makes it complicated. Right? The goal, though, when you're doing the substitution, there will be multiple things you can substitute. Your goal would be to substitute something where it makes it simpler and the derivative is somewhere else in the function. That brings you to step 2. Substitute u and du. This is the derivative of u into the integral you're doing a change of variables, so the only variables should be u. And basically now you compute it, compute the integral. Why? Because at this point the integral would be a lot simpler. It will fit a basic rule of compute. You'll get an answer in u. So what you do is you call it a back substitution. So you're going to substitute in the reverse and get the original expression back and plug it into u. And then at that point you're done. So let's actually do an example. Let's do this example so you can see what I'm talking about. So that's our function. We want to find the antiderivative of that, the integral of that. Same thing. Doesn't look like a basic rule, can't simplify it to look like a basic rule, nowhere to get rid of the radicals so I can distribute and use the power rule. So we're kind of stuck. So whenever you're in that situation, you realize, oh, substitution. How do you know you have to use substitution? It's literally the only other technique you know. We're not going to learn anymore, it's just this one. Like if a basic rule doesn't work, substitution is what you're going to do. So that makes it a little bit easier. In another class, there's a whole process where you have to figure out what's the best method to use. Here it's easy. Doesn't fit a basic rule, use substitution. So the idea is here, we want to substitute an expression that makes this simpler. So let's take a guess what he is.
1 plus x squared.
Right. That was the guy that made it complicated, because that's under a radical and it's a sum. I can't get rid of the radical with that sum under it. That's complicated. So I'd say u equals 1 plus x squared. Do the substitution. Right? So now if I just replace this with a u, that's simple. That's just u to the 1/2. That's incredibly simple. There's just one thing under the radical. So you realize that, hey, that would actually make things a bit easier, but we're not done. We need to also make sure the derivative is somewhere else in the function. So now what I would do is I would take the derivative of both sides. So I can take the derivative of the u with respect to x. Derivative of this side here is 2x. Right? Now for the most part, we can ignore the constant. As I said, being off by a constant factor doesn't matter. But what about this x? Is this x somewhere else in the function? Yes, it is. It's right there. It's important that the variable part of the function, you can find it somewhere else hanging out, separate from the u. So the u is going to be over here. The piece that when you differentiate it should be somewhere else, right? A factor somewhere else. Otherwise, the substitution is not going to work because you have that x left over and you can't replace it with anything. What we do is, usually we don't write it like this, we multiply by dx, so usually you jump to this step and think of it as 2x dx. But after this point, there are a couple ways you could do it, but in my experience, students prefer to do it this way. They solve for the dx. Right? So you get u equals 1 plus x squared, du equals 2x dx. Then you solve for the dx. So the dx would be 2u du over 2x. So this is the step one where we're going to substitute. Right? And we have to change everything, right? So we have to figure out what's going to be our u. We're going to have to change the dx into something else. Now we're going to move on to the next step, which is to actually plug this into the original integral and rewrite it. this gives us the following. This expression here I replaced with u. So that's just the radical of u. The x, I didn't really replace that with anything, so that guy is hanging out. But my dx is now du over 2x. And now what happens? Notice here, the x's will cancel. So I'm just multiplying a bunch of things. Here's that 2 in the denominator, but it's just divided by 2 same as multiplying by a half. I can literally just factor it out, put it on the outside. And so that's what I have left. Now you look at this guy compared to this guy. This was very complicated. This one is simple. Why is it simple? It looks like a basic rule that we have. That's just u to the 1/2. It looks just like the power rule, except it's in a different variable, u. But that doesn't matter. The process is still the same. Like if I'm integrating with respect to u, use my variable, I can still apply the power rule. That'd be u to the 3 over 2 times 2/3. And so that would be 1/3 u to the 3 over 2 plus c. Or in other words, that would be, and so at this point is where you do the back substitution. This is your answer, but that's your answer in terms of u when the question was posed to you in terms of x. So what you do now is afterwards, step 2 was to plug in, and step 3 now is to back substitute. So plug in and compute. So the idea is once you plug in all these numbers, you should get a much easier integral that fits your basic rule. You do perform the basic rule, you'll get an answer in terms of u. But what is u? You were asked a question in terms of x, so you have to put it back. So essentially, wherever you see u, you're now going to replace that with 1 plus x. That's called a back substitution. 1 plus x squared. And that is the answer. And you would realize that you can actually check this, that that's your answer. Right? If you differentiate this guy using the chain rule, you can actually get back to that guy. Right? The 3 over 2 will come down, the 3's would cancel, you'd be left with a half. Subtract 1 from the power, you get 1/2, which is the radical. Then you multiply by a derivative of the inside, which is 2x. The 2 is going to cancel the half over here, so it's just an x that you can move in front, and so that's your guy. The derivative of that expression, the derivative of this is that. So we found the antiderivative. And the trick here was a substitution. It was very complicated in the beginning. Substitute the thing that makes it complicated. Hopefully its derivative you can find somewhere else in the function. If you don't, it means you did a wrong substitution. It means there might be several things where you have the option, maybe this, maybe that, but the one you choose needs to have its derivative somewhere else in the function. That allows you to rewrite the integral in a very simple way. After figuring out what is the u and the du, you can apply a basic rule and then back substitute to get to the answer. So a few more examples. I think we managed to get to the 3. This one, e to the x over 1 plus e to the x. This one, 1 over start with the first one. Ideas. Yeah?
Set u equal to 1 plus influence.
Okay. So notice here that denominator is kind of what making things complicated. Why? You can't split a denominator. You can't split a fraction across the denominator. So if you have a sum of fraction, you can't do that trick that we did last time and just divide into each. It makes it very complicated to actually do that. So that's really messing things up for you. So you decide to say, okay, let 1 plus e to the x be my u. Now I can find the derivative of that, du is just e to the x dx. And I can notice that my e to the x dx is right there. So if this is my u, this is my d. I can solve for dx, du over e to the x, and then I can plug that in. So I go back to my original integral. E to the x is just hanging out. The denominator I replace with u. The dx I replaced with du over e to the x. The e to the x's, of course, cancel. And so I'm left with integral of 1 over u du. And that's a lot simpler. It fits with one of our basic rules. What is that?
ln of absolute value.
ln of absolute value of u. That's our answer in terms of u. They asked us in terms of x, so we have to put it back. ln of 1 plus e to the x. What about this one?
Set u equal to 4 minus x.
U equals 4 minus x. Because that's what was making it complicated. If this thing were a single variable, if it was just the radical of x, I'd just bring it up, write it as x to the minus a half, and then I could do the power rule. But because it's a whole expression, I kind of have to, I couldn't simplify that algebraically, so I'm doing a substitution. Change this thing into a single variable so it's easier to deal with. Find my derivative, du would be minus dx, because the derivative of that is minus 1. Which means that minus du is equal to dx if I solve for dx. And so now I can plug everyone in. So this is 1 over the radical of u. And my dx, this guy, becomes minus du. I can factor that minus out. I have that expression, which at first might look a little complicated, but it's really just e to the minus 1/2. And so I can apply the power rule. Add 1 to the power, divide by the new power, plus c. I can plug that in. 4 minus x to the 1/2 plus c. And you can, again, you can check this, that if you differentiate that, you do get this stuff. What about the last one? Yeah?
Would you substitute 5 plus x squared? Or could you do either?
What?
Could you substitute for either one?
What do you mean?
Either 3x or 5 plus x squared, if you wanted to.
Okay. What if you did u equals 3x? What would have happened? What would the du be? 3dx.
Yeah.
you see an issue? There's a whole part of the function that is not in my derivative. I wouldn't be able to swap that out,
Okay.
right? Now technically you could say that if u is 3x, then you could plug in x equals u over 3, and so you can replace that x with u over 3, and so you get something that looks like this. But that's not any simpler. It's like you pretty much ended up in exactly the same situation. So not all substitutions are created equal. The two things that I asked you to look for, they're actually important that you have them. And for the record, I'm not saying anyone will ever do this, but u equals x is always a bad substitution. Why? Because you're literally not changing anything. You literally go to the thing, and everywhere you see an x, you add a u. That's essentially what would happen. Like, so if you say u equals x, right? There are times when u equals a constant times x might make sense, but in this case it didn't, because it didn't really help simplify anything. And the fact that, and you can kind of knew that that's what was going to happen by when you took the derivative, the other part of the function. So if this is my u, the other part of the function was not in my derivative. Once you see that happens, that's kind of a red flag. It means I probably didn't choose the right thing. So you do want to make sure that your derivative is somewhere else. So yes, your first suggestion would be the way to go. You would substitute the u equals the 5 plus x squared. And so how you can be confident that that will be the right thing to do is when you differentiate that, you get 2x dx. And so you care about the variable part of the derivative, and there it is, right? So if this is your u, the leftover part of your function is a part of the derivative of the u. And that's what you have to look for to make sure things swap out nicely. And so you can solve for the dx at this point. That's du over 2x, and then you plug it in. So the 3x I didn't do anything with. The denominator I replaced with u. The dx I replaced with du over 2x. The x's cancel. 3 and 2 are constants. I can factor them out. And so I end up with that. It's a guy we've seen often before. So that's just your ln of u. And then I replace the u with what I substitute in the first place. So it's 3 over 2 ln 5 plus x squared. That would be our answer. And we'll stop there, because that's where I got up to in the last class. So we did 5.1, 2, and 4. 5.3 isn't in our syllabus, so that's where we are. So remember we have a test on Friday, and the review is already up. And the solutions for the review is up. So I'll see you guys then. Oh, the test.
Yeah.
Francesca?